Hello and welcome to the Cisco AI Insights Podcast, where every month we invite a technology and AI expert to the show to highlight and discuss trends, news, and academic papers from the worlds of AI, machine learning, and data science. I am one of your hosts, Rafael Herrera, and my co host is a machine learning engineer and data scientist in Cisco's customer experience team. Welcome, Sónia Marques, to the show. How are you doing, Sónia?
Hi, everyone. All good. Very excited for this session. I think everyone will find it very useful and insightful.
Today, we are discussing a topic that is very interesting, and I can't wait to learn more about it. And that's why we brought on the one and only James Tidd onto the show. He is a Cisco AI operations engineer. James, welcome to the show. How you doing today?
Really excited to talk about my topic.
Today, we're talking about small LLMs, and obviously, you're the guy that knows all about this stuff. You've been tinkering at this for, is it years, decades, or just months?
I'd say around a year or so I've been tinkering with it.
A year or so. That's a lot to tinker with something like this, but please walk us through what is a small LLM, because there's so many ways of looking at it. And the way I've understood it as I keep up with this AI stuff, they're billion parameter large language models. Is it just a million parameter large language model, or is it more than that?
Well, I mean, to be very facetious, small language model is just what it sounds. It's a smaller version of a large language model. These larger models like ChatGPT and Claude and the like, they can have up to 1 trillion parameters in their models. And these parameters are just little knobs and dials that are learned behaviors. So when you pass through some information, they pass through all of these trillions of parameters, something predicted comes out on the other side. And you can apply this to something with a lot fewer parameters. For example, like you say, tens of billions of parameters instead of trillions, or 5 billion, or even millions, tens of millions of parameters. And these models work in exactly the same way as a large language model. They just have a lot less information stored within them.
Would it be like you're putting a wrapper on a normal LLM essentially and just shrink wrapping it, or is it actually a smaller LLM?
So they are smaller, they have a lot less parameters, but you raise a good point because some of these small language models are designed to be distilled from larger models. So they are trained specifically to mimic a larger model. But you may also have small language
Yeah.
models that are specifically designed for a certain use case.
Yeah, I think it would be nice for us to just go over high level the concept of knowledge distillation. I think that would be useful for this topic here to explain.
Sure, knowledge distillation is the idea that, well, in the case of large language models, that you are trying to distill the knowledge of a larger model, which has these trillions and trillions of parameters, down into a smaller space, something that maybe contains only 10 billion parameters. This is useful in terms of LLMs because it means that you might have a general task like a chatbot that maybe doesn't need to have every single little bit of information the large model has. But when you talk to it, it sounds good enough. Maybe you couldn't even distinguish it from any topics.
Yeah, and based on the assumption that perhaps even these large knobs that we're turning into these large models are a bit redundant, these knowledge distillation techniques could be very useful to make these models more efficient, maybe lose some of the generalization that they have striped.
Absolutely. Like you say, maybe you don't need all of those knobs and dials to have a model that predicts something as good as a larger model or close to. And the paper I'm talking about today is called Fast Inference from Transformers via Speculative Decoding. And it's using the knowledge that these models have maybe far smaller footprints and are far easier to run, but might be able to predict words and tokens or close to, as well as a larger model. This paper looks at how we can use these smaller models to potentially speed up how quickly the larger models can infer tokens or next word prediction. And this would be for the end user on ChatGPT, for example, how quickly these models are spitting out words, which not only is a nice user experience, but has implications on how much energy these models might be using up, which in the current news is a pretty big deal. There's lots of data centers coming up. A lot of these data centers are running model inference. So perhaps people might want to save a little bit of money.
So to clarify that just a little bit for me, if we are running an LLM, we obviously have a lot going on behind the scenes to get the answer to who was Batman in 1989, right? To ask it something dumb, we have a lot of power going into it. And essentially, on the back end, it is guessing the next word, what is the next character, the next token to be more official, and running those calculations in the background is what is slowing the whole process down. And apparently, this paper has a way of doing it a little bit differently, more efficiently, maybe.
Yeah, you've pretty much got it. So when you have a model with trillions and trillions of parameters, each forward pass, each time you are using the model to predict the next token, you've got to run all of the previous tokens or words through the entire model, every single word that you predict. And the larger the model, the more computationally expensive that is. The primary observations that this paper makes is that when you're predicting these next tokens, some of them are perhaps a little more easy than others to predict. So, for example, if you ask a model, what is the square root of 7? It's quite easy for the model to predict that the square root of 7 and the 7 itself is probably going to come up. But if you were to actually want the answer, which is 2.646, the model within all of those parameters needs to somehow store that information. And so it's conceptually more difficult or harder for the model to predict this. Perhaps it's not even within, for example, a smaller model's parameters. That information might not exist for a large language model. It's constrained by memory, so by VRAM, video RAM, not the compute. The hardware that these models are running on is extremely, extremely fast. The transformers for a forward pass through the model only need like 1/100th of what the GPU can provide. And these are the two main points to think about for the rest of the conversation.
When I think of a computer doing all of this LLM magic stuff in the background, obviously you mentioned VRAM, that's part of your GPU, right? So what is compute if it's not VRAM? What are we saving here? What are we working with?
With a large language model, these parameters are stored as weights, and these weights are essentially just floating point numbers. So numbers, you can think of them like very, very long decimal pointed numbers in a way. It's not a great comparison, but it's a good visualization. And the video RAM stores all of these weights, and these can take up tens to hundreds to terabytes of storage. For a model like GPT, you'd need maybe thousands, hundreds of graphics cards to store these weights. But critically, computing the actual inference doesn't use nearly as much of the graphics card like available compute than the VRAM does. The VRAM is going to be full, but you've essentially got all of this compute available that you could run other tasks with if you wanted to.
So it sounds like there's this trade-off between two specs of the hardware that we have. So how does your method orchestrate this trade-off?
The paper takes kind of an old idea called speculative execution, which is used in CPUs, has been for a long time. And essentially what it does is guess or pre-compute some operations in the hopes that it gets them correct and perhaps speeds things up. What this paper does and what's novel about it is it applies this idea to a probabilistic space like a large language model, where the tokens are given in some probabilistic manner. If you change the temperature perhaps of the model, you might get a slightly different answer because the model's predicting a probability and then choosing from that probability of tokens. The paper looks at how you might apply this specifically to transformers, the technology behind large language models, but also for general probabilistic space problems. They do this with the idea of using a smaller and draft model, so a small language model, to predict what the next few tokens of the large model might be. And where the efficiency gains come from this is that the draft model can predict tokens way, way more quickly than the larger model. A larger model, perhaps in this instance, might be a 70 billion parameter model, but we use a draft model that is maybe a billion parameters or 100 million parameters to try and predict the words or the tokens that the larger model may be saying for a given input.
Now, an interesting way that I believe you helped me understand this a little bit more clearly is almost like a paralegal kind of comparison. Could you explain that a little bit, what you mean by that?
In that sense, it may be like you have a task that a lawyer or perhaps an editor of a newspaper needs to complete, in the sense that these larger models are more computationally expensive. Maybe it's more expensive in terms of paying a lawyer to write out a specific task or do a specific problem. Whereas you could have a smaller or cheaper person do their best job at predicting what the larger model or the larger lawyer or the person above might want. And if the smaller model, the draft model, does a good enough prediction, perhaps this larger model can use some of the words or some of the text that the smaller model has produced, saving loads of time because the larger model doesn't need to go through all of its parameters in order to get to an answer. The smaller model has already done it for them.
This kind of reminds me of, it's almost a really meta idea, and I don't mean the company, just in concept. It's almost like how I use things like ChatGPT, because I could spend a whole bunch of time crafting one paragraph about something, but I just jot down a few ideas and I let ChatGPT fill in the blanks, and then I look at it again, and then I'm like, oh, yeah, that's good enough. And then I alter a thing or two, but then boom, and I just wrote that paper or whatever in 5 minutes instead of the 1 hour that it would have taken.
That's a great analogy. This paper relies really on this draft and revise dichotomy. We don't need to spend so much power to do the simpler task. We just need the smarter one in the room to revise.
I think that's a
Like,
really fun way of thinking about it. What the paper really goes into and talks about is the fact that you need this draft model, this smaller model, to be as close to the larger model as possible. The paper goes into a lot of detail on how, if you are able to make the ratio of correct answers that the draft model predicts to the accepted answers as good as possible, that you can make this speed up better and better and better.
yeah, makes sense. So basically, the draft and the target model need to be as aligned as possible. Even though the bigger one knows more, the smaller one will
So
agree in most of the general terms.
why not then just have two of the same model? Let's say it's identical, but one is working as an intern to the other one's being the hotshot executive. Why not just have the exact same one? Obviously, it sounds like it's going to be a lot of power and a lot more juice, but what's the difference between just using two models to achieve one job compared to this method that you've described?
Yeah, that's a good question. And it goes back to this spare compute, right? So if you were going to be running two of the same model, you might need two GPUs, two graphics cards, or maybe you need 200 instead of 100. It's going to be double the resources. But as we talked about before, you have this trade-off of VRAM and compute. So if we take the example of a single GPU that has maybe 140 gigabytes of VRAM, but 80% of the compute left, you can take a little bit of that VRAM away, perhaps by reducing the allowed total size of the prompts that can be fed into the model. And then you can take that compute almost for free and run this smaller model. So instead of needing two GPUs, in your example, you only need one. And so you can get this speed up without sacrificing some hardware or power.
That sounds pretty good to me, especially with how expensive all that stuff is.
I was wondering, James, did you have like any hands-on experience with something similar to these techniques already?
This paper came out 2 years ago, which in LLM terms is decades. But since then, there's been a massive amount of research building upon this idea. And one of those is the Eagle project. Now, the first two Eagle releases didn't use a draft model. They instead trained the bigger model to just be able to essentially predict tokens for itself. But Eagle 3 uses a very similar method that's discussed in this paper. And the Eagle framework allows you to train a very small model off your own or an open source bigger model. So, for example, you may have an 8 billion parameter model. You can use Eagle 3 to make a model that is maybe 200 million parameters. And some of these are available online to test out. And if you search up Eagle, you can do so yourself. And that's something we did. On one of our clusters, I tried this out with an 8 billion parameter model over just a generic 80 prompts or so. After following some of the instructions in the paper, how to get it set up, which was very easy, I was able to reproduce a 3.4 times speed up using this method. And this is quite a bit better than the paper that we're discussing now. And you can look at Eagle as to why that is. But this paper also predicts a theoretical maximum of maybe 6 times, but realistically, these methods are in practice already providing speedups of up to 3.8 times.
Really impressive. Paper looks to me like a reaction of the industry to the need to reduce costs. I think up to now, with the competition between so many huge companies, there was a bit like bloating of these models and their sizes and the crazy compute that we need to use. And now I think the trend is maybe to go more in a simplistic way, maybe with a bit more orchestration. In this case, see where we are over engineering and overusing resources.
Yeah, for sure. The amount of power that these data centers use is pretty extreme. And perhaps this could either speed up current models, allow you to run current models more efficiently, or perhaps it could allow you to run better models, but at the same speed as the current models. And one thing to note, and perhaps those who are listening might have thought about already, is that when we're making these predictions with the draft model, we might be saying, oh, does this reduce the accuracy of the overall system, the overall prompt? But I wanted to point out that if you go and read the maths in the paper, it can be quite a lot to take in. The probability distribution using this method is actually exactly the same as if we use the main model. And so we're almost getting these speed ups conceptually for free, which I thought was quite cool.
I believe we might have answered this, but just for the sake of clarification, how is this different from something like a thinking model? Because my understanding is that in that situation, it's one model that is just thinking through the entire thing to give you the answer, but it's just singular, where the advantage is still in accuracy. Would that be a good assessment of that? Am I totally wrong here?
Oh no, I think you're completely right. So this, in theory, would not care if you are using a thinking model or not. So a thinking model is trained to have this thinking block, which can help you get more context out of the model. And if you were to use this for the thinking model, you just need to make sure that your draft model was trained up alongside the thinking model. And as long as that ratio between the correct answers and the false answers of the model is good, in theory, it would work just as well with a thinking model.
Yeah, it's one of the advantages that is mentioned in the paper. To use this method, we don't need to retrain any model. We can pick and choose which models or pairs of models we use with this technique and take advantage of this framework.
Exactly. So long as the smaller model is good at predicting the larger model, it's agnostic. It doesn't care.
Obviously, this came out 2 years ago, so this was not long after ChatGPT launched. It became very mainstream, so everybody was throwing things at the wall to see what would stick, really beefing up things, as you described earlier, and we are refining and making things a little bit better. But how do you believe, just you, not the paper, but you personally, what do you think is going to come out of this? How do you think we can really utilize this to maximum effect?
Well, this particular paper was written by the kind folks over at Google, and based on some of their blogs, it seems that this is already being used to speed up inference on their search engine generalization or summarization. And so it's already being used in practice to speed things up. But like we discussed earlier, there's a few ways this could go. Either companies might want to reduce costs, Or, in my opinion, probably they want to run better models just as quick because ultimately their customers are concerned about how good the output is.
Essentially, what you're saying is we could run what we have now in a more streamlined way that uses less energy, that is equally accurate. And if we wanted to, we can take the next step to make it more accurate for the next one, but we don't have to. We could literally just keep what we have, but just make it run smoother, faster, stronger, all those things.
Yeah, exactly.
Yeah, more environmentally friendly.
Yes.
Yeah, that'd be nice. And looking at it from a business point of view, you see how things like RAM and GPUs are getting very expensive. If you are just a small organization trying to keep up, this could be a method to not have to expand too much more and actually do more with what you have already. So it seems like a pretty foundational paper.
Yeah, absolutely. And if you follow the space since this came out, I think it was officially released the end of 22 and then revised in May 2023. There are now tens to hundreds of research papers that build upon this, Eagle being one of them that we mentioned earlier. And I don't think that it's going to be slowing down anytime soon.
Okay, so if you're listening to this and you're out there and you want to do more with less, it sounds like James brought you the perfect paper to use in your own data centers, wherever it is that you're doing that. With that, thank you, James, for coming around and showing us a better way of doing things, a more efficient way of doing things.
Of course, thank you so much for having me.
And for everybody listening, if you like conversations with experts like James about AI, machine learning, and all the other emerging data science technologies rapidly changing our world, please subscribe to the feed wherever it is that you get your podcasts. We are on SoundCloud, we are on Spotify, and we are on Apple Podcasts. So search for us. We'll show up there every single month with a new episode talking about whatever the world of AI is throwing at us. And until next month, thank you for joining us. I am Rafael. I've got Sonia, and we have the wonderful James with us. Thank you, and we'll catch you next month. Take care. Bye bye.
Bye
Goodbye.
bye.